All right, we're ready to start the next one, which is polynomial time and dependent types given by Robert Atkey.
Okay, thank you very much. So this is some work that is pretty much just putting together two things. So it's one of those papers where you just think, I've got one idea, I've got another idea, and I'll try and do them together, see what happens. And I think what happens is quite interesting. So dependent type theory is a programming language, and some people think that you should be able to write programs in it and actually run them, and maybe one day this is what all programming languages should be like this. And it's also a proof language, so we can write programs and we can reason, but we can only reason really about their extensional behavior. And like we can sort of pretend that we're going to reason about the way they operate because we can encode things. Like we can use monads to sort of surface effects, or we can use tick monads to surface the consumption. But what I'm going to talk about here is a kind of way of talking about the intrinsic costs of programs. So what if we want to talk about a program's complexity? And there's quite a large design space here. So one thing I alluded to there is, are the costs sort of extrinsic, are they user-defined, or are they intrinsic? So do programs consume resources by some kind of tick effect, like we saw yesterday in the decaf work? Or do they simply consume resources just by existing and executing? Do we want to do explicit or implicit accounting? So do we want a statement at the end that says something like, this program takes exactly n squared plus 3 and 12/27ths of an n times n steps if the input is size n? Or are we happy with a statement like, this is a polytime program? And another important thing that comes up when doing this within a theory which combines the programming and the proof is, how do we mediate between the intensional and extensional meaning? So how do we stop the costs interfering with the behavior? So if you naively do the thing with the tick effect, then you can sort of end up making the program depend on how long it's run so far. And there's a really clever way of doing that in the calf and decaf work to stop that happening. So in this work, what I've done is chosen a particular space in point in the design space, which is implicit polynomial time by linear typing, combined with extensional program reasoning with dependent types. And I think this is an interesting combination because, and I think this is sort of possibly slightly delusional, but I think what this might lead to is some kind of synthetic kind of computational complexity theory, where we can do computational complexity theory, but without, I know this is the Turing room, without talking about Turing machines directly or anything like that. So, but there's a question mark. I mean, maybe this will work, I don't know. So this paper is just putting these two things at the top together. So first I'm going to talk about implicit polynomial time by linear typing. So this is quite an old topic, but I'm just going to introduce a way that I'm going to talk about doing it here. I'm going to show you two different ways of doing it. So why are we interested in polynomial time? So probably most of you went to a course on computational complexity, and they said polynomial time is feasible computation. And then you immediately thought, well, what if it's n to the 100? It's not very feasible anyway. But the sort of reasoning that goes here is that feasible computation should be closed under, we're allowed to iterate over the input, right? So take the size of the input, and we're allowed to do a number of steps linearly proportional to that, at least. And we should be able to compose two feasible computations. Like feasibility should be closed under composition, probably. And this one's a bit iffy, nesting of iterations. So it should be sort of closed vertically, if you like, as well as closed horizontally. So let's build a type system for polynomial time, and we're going to use linear types. And the key kind of points here is we're going to separate iterable and non-iterable types, because remember both the big thing in the previous sort of list of constraints was that we're going to control what we iterate over. So I'm going to have an iterable type of natural numbers at the top there. And you'll notice it's linear, so in the zero case and the successor case, there's no extra context. We have to, for whatever information we want to pass through, we have to pass through in the type A, and then we have a natural number, and we can do iteration on it. And let's say we also have a non-iterable nat, so these kind of hollow nats with the little empty circle, and we're only allowed to do case analysis on those. So we're going to separate these two kind of natural numbers. And now, basically, the way to get feasibility is some kind of NIMBYism, right? We're just going to ban construction of natural number values. So we're allowed to construct these hollow naturals that we're not allowed to iterate on. but any natural number that we iterate on must come from the input, must come from the outside. So yeah, we can construct non-iterable natural numbers. We are allowed to duplicate natural numbers. This allows us to nest iterations. So the reason for banning construction is we can't use the input to get bigger and bigger natural numbers. So you can once you can iterate over the input and you can create numbers, construct them using successors, then you can sort of define addition, multiplication, and exponentiation, and so on. And the sort of slightly amazing thing is that just with these things and linearity, we get a system that's sound and complete for polynomial time. Let's call this cons-free system. And a crucial point is that the linearity. So like I said, oh yeah, we can duplicate natural numbers, but what we can't do is duplicate things at higher type. If we could do that, then we could sort of encode constructors in some kind of church encoding kind of thing. So we're not allowed to do that. So this system isn't very much fun to actually program in, because you get the natural number or whatever input you have that has some kind of size, and then all you can do is iterate over that. So in theory, yeah, you can do enough kind of steps to simulate a Turing machine, but it's not much fun to program in. So Martin Hofmann, about 25 years ago now, came up with this LFPL system, which stands for Linear Functional Programming Language, that allows transmission of this iterability via diamonds. So we can now construct iterable natural numbers by paying a diamond for each constructor, and then when we iterate over them, we get the diamond back. So in the zero case, we get a diamond. In the successor case, we get a diamond. And then this allows us to then reconstruct sort of smaller natural numbers underneath that we can then do nested iterations with. And again, this is sound and complete for polynomial time, as long as you also have these non-iterable data structures as well. And also here now you cannot duplicate the natural numbers. Okay, so that's two simply typed systems for doing implicit polynomial time. So the point is that these are both sound and complete for polynomial time. You write your program, if it type checks, then it's guaranteed to be realizable by a particular term that will always run in polynomial time in the size of the input. So how do we combine this with dependent types to be able to reason about programs? And so this is tricky, because in type theory, the variables are used as sort of mixed usage. Some are logical, some are computational, some by logical I mean they're just used there to make sure the types are well formed, but they play no role. So like the previous talk, we have some members of the context which are only there to make sure the types are well formed. They're not computationally relevant. In linear logic, we have things in the context, and their presence or absence means that if it's not there, we can't use it, but if it is there, we must use it exactly once. So we might have something like the X in the type theory context is sort of only used in the types, so then is it really used in the term, or maybe it's used in the types and the terms. So this makes a kind of naive combination of linearity and dependent types quite difficult. So there's been many solutions to this. I haven't got time to go through more here, but I'm going to talk about one, which is this quantitative type theory. So the idea is sort of taking ideas from sort of simply typed or polymorphically typed systems where we annotate the variables in the context with how they're used, and we do it from some semi-ring R. So you can do this with, for instance, sets of principles, and you can get information flow typing. Now, Conor McBride's sort of insight was, well, zero usage is very useful here, because if you annotate something with a zero from the semi-ring, you're sort of not using it in some sense, right? And so this is sort of precisely what's going on when we're just using variables for their meaning in the types. So let's say we allow any kind of zero usage data to appear in the types. And if you follow through this idea, you come up with a system where, in addition to having annotations on the variables, we have one on the term as well, so this sigma at the end. And this kind of splits the type system into two sort of separate systems. Then when we have sigma 1, this is like the real computational world, and sigma equals 0, it's the types world, the world where we're allowed to do unrestricted computation. And this means that we can do linear typing in the sigma equals 1 fragment, but then there's always a rule that always says if we have something in the sigma equals 1 fragment, we get it in sigma equals 0 fragment, and then we can reason about it there. So I'm going to take one of the systems from earlier, the LFPL one, and combine it with this quantitative type theory. So the first thing we have to do is add diamonds. So we have a diamond type. And now we're allowed to construct diamond type, values of diamond type, but only in the sigma equals 0 fragment. So at the type level, diamonds are free. At the term level, the number sigma equals 1 level, we have to pay for them. And we even have this rule that says this value is unique. So the diamond acts like a kind of unit type. Then, yeah, we have to pay with diamonds for constructing natural numbers. And then the important part is this scary rule, which is the eliminator now for these things, which is now dependent. And we annotate the bits, so these red zeros are where we have information which is only available at the type level, but not at the term level, not for the term level. So here we need all these extra gammas around to make sure our types are well formed in all the places. And we're dependent eliminator, so we've got the 0 and the suck substituted in for the x in the type of the sort of induction hypothesis. And as I said, diamonds are free at the type level, so we can just put star in for the diamond values at these points. And when we're in this sigma equals 0 fragment, all the diamonds are free, so this just acts like a normal NAT iterator. Just want to say the soundness, simplified, is if you have a term like this, then there is a term in another calculus which realizes it and always runs in polynomial time. And for what I want to do next, an also important thing is if we have a term or something that we can construct in the sigma equals 1 fragment, we can reflect that back into the types with this kind of realisability type. So this RA says all the values of A which are realisable within the linear, the sigma equals 1 fragment. So in particular, this is going to mean if A is nat to nat, then RA is going to be the type of all terms which are polynomial time functions from nat to nat. So that means we can then use this system to sort of define some notions from complexity theory. So let's define a problem to be a pair of A in the universe and a predicate on A. So this is like problem instances, and these are decision problems. This is like the ones which are solutions. We can then define p time to mean that there is a decider, f, which is realizable in polynomial time, such that for all instances, if it says true, then the predicate holds. We can also define polynomial time reductions. So if you're sort of looking at this with certain eyes, these are containers. These are sort of like the Cartesian container morphisms. And yeah, so it sort of speaks to a general kind of conception of containers as question-answer pairs, and container morphisms as reductions between them. But now we're doing it in polynomial time. But okay, we can define p time, that's not unexpected. If we now add the effect of non-determinism, then, and this idea of like non-deterministic computation, we're going to witness a list of Booleans, and maybe it gives us an A at the end, assuming we've got enough Booleans, then we can define the class NP, right? So we can define it as the problem is in NP if there's a non-deterministic polynomial time computation such that something is in the predicate if and only if there exists a witness that we can supply to the non-deterministic choices. And further, we can define a sort of simple probability finite distributions monad, define what it means for that to sort of have what the probability of it returning true is if the leaves are Booleans, and we can define the class BPP of probabilistic problems where it's guaranteed to return the right answer of probabilities at least 2/3. And this is quite sort of shows why we want to combine dependent types and this implicit computational complexity, because we now have to specify this kind of semantic constraint. Okay, so to conclude, what's in the paper? So there's the full description of the systems, a bit about programming, and a description of the soundness proof with its Agda formalization. What next? Some more complexity classes, polytime circuit generators. I think the interesting thing is what is needed for a proof of NP completeness. So the thing here you actually need is to be able to get the source code of the program in order to encode it in 3SAT. So some kind of extra axioms about this realisability thing. Application to formalized cryptography. We can now quantify over all polynomial time probabilistic computations representing the attacker. And also an extension of the system to explicit resource accounting. So you can actually count the number of diamonds that are being used. Okay, thank you very much.
All right, we're taking questions, and also the question being cut, the author actually responded on Discord, so we take a look. Okay, so we have one question in the middle of the audience, also here.
Thanks for the talk. So I would like to ask, have you thought of connections to descriptive complexity? Because, I mean, there's, for example, this characterization of classes like P, NP, and so in terms of logic. And I'm not an expert in type theory, unfortunately, but I thought if by the Curry-Howard isomorphism or something, there could be some interesting connection with your work as well.
I would like to know, yeah. I mean, like,
Thank you.
Yeah, I don't know.
We have one more, but I think this person.
So, have you formalized something is NP complete or something like that?
No, as I said.
So that's the simplest one that you.
So the problem there is that if you want to take I've got a description of a Turing machine which runs non-deterministic Turing machine that runs in polynomial time, then you need the source code of it. So it's you want to sort of take anything which is in that description of NP, get its source code, and convert that into a 3-sat problem. So there's some kind of reflection required there.
Sorry,
Okay. First. Oh, okay.
So I think around 2015 there was this notion called NP mightiness, which was developed about the simplex algorithm, and basically the idea is that if you look actually inside the bits of the simplex algorithm, it's inefficient, but it's solving a harder problem than the actual linear optimization. And so one of the appeals of thinking about this work to me is that you can actually look inside and see what the intentional behavior of the programs are and see if they're actually working harder than they need to be. So can you look inside of the specific the composition of the specific functions that you're using and seeing what kind of behavior they have themselves?
No more than you can by the fact it's a program and you can look at the source code.
Okay.
Yeah. The types are kind of like everything says just this is polynomial time. It doesn't tell you any more information. Maybe with the explicit one, maybe.
Yeah.
Okay.
If it's a student, I can.
We already have like 3 and 1 more question in queue, so yeah, please just continue. You're fast. Who is the next name? No, the online come after them. Yeah, sorry. Well, our queue is already full. But we can. You're encouraged to continue the conversation on Discord, and I believe Rafael will take a look.
If I had a more restrictive idea of feasibility, where I thought n was feasible, but n to the 500 was not feasible, is there a way of, would it be easy to extend this to index the types by giving an actual count of how nested the iterations are?
I thought about it briefly. I think so, and it gets incredibly fiddly. But yeah, I think so. Like you basically have to annotate the types involved in the iteration to stop you when you've gone too far. You're not allowed to nest them too much.
I think we can take one more because there are no more talks after
I
this.
just want to ask briefly about your comment that it's not very much fun to program in calculus. I mean, the criterion of sound and complete for polynomial time is pretty coarse because you can just, to simulate a Turing machine, you just need bits. You don't need any kind of interesting data structure or anything. So how far do you think you are from capturing natural polynomial time algorithms, and is that an interesting direction for the work you're doing?
I think it is an interesting direction. I think there's been quite some sort of practical work using LFPL to actually program with. So it was actually in the context of the fact that you can also interpret the diamonds as memory cells and it's all in place. And there's work on writing like reasonable programs in there. So you can write sort of sorting algorithms and things quite easily. Whether you could get a good library of polynomial time things, I don't know. But yeah, I mean, to actually use this, I mean, the point is that when you can do these polynomial time reductions, you actually want to write things you're interested in. And programming with graphs in functional languages is already a pain anyway. So maybe this is the right, if that's the kind of thing you're doing.
All right, let's thank the speaker again.